అవును అది సౌండ్ రాలేదు. అంటే యూట్యూబ్లో రికార్డ్ ఇది యూట్యూబ్ ఇచ్చినాము నా రికార్డు కొట్టలేదు లైవ్ ఆన్ యూట్యూబ్ లైవ్ ఉంది కదా సార్ ఫోన్ చేసిన వస్తా అన్నాడు అదే ఆన్లైన్లోకి అందుకే ఇది దగ్గర పెట్టిందా నేను ఓపెన్ చేస్తాను సార్ అంతా ఓకే కదా నువ్వు జాయిన్ అయితే కదా నీకు పైన ఉన్నా అంతా నీ సొంత దాన్నే చేయడంలే నీకు లింక్ పెడతా వాట్సాప్ లో జాయిన్ అయిపో మెయిల్ పెడతాలే మెయిల్కు 10కి
లేకపోతే సాయంకాలం కలెక్ట్ చేసుకున్నామంటే కలెక్ట్ చేసుకున్నాం.
हो सकता है जाऊं,
है
हो सकता है जाऊं।
దేంట్లో రికార్డ్ పెడతాం కంప్యూటర్ అదే అదే పోస్ట్ చేయాల్సింది దాంట్లో జాయిన్ మెసేజ్ అలో చేస్తున్నాం.
సార్ సిద్ధారెడ్డి సార్ వినిపిస్తుందా?
వినిపిస్తుంది సార్.
ఓకే ఓకే అన్మ్యూట్ చేసుకోమంటావా?
అన్మ్యూట్ చేసుకోండి. మ్యూట్ లో ఉన్నారా? లేరు కదా మీరు?
లేదు, ఇప్పుడు మ్యూట్ లో ఉన్నా. ఇప్పుడు
లేదా అన్మ్యూట్ లో ఉన్నాను. అసలు అన్మ్యూట్ చేసుకోండి.
వినిపిస్తుందా నా వాయిస్?
అట్టే ఉండండి మీరు. ఓకే
సరే.
There you can type, you can search different type of books, e-books. You can easily search.
अच्छा
నమస్తే చెప్పు కిషోర్ భాయ్.
సార్ గుడ్ మార్నింగ్ సార్. అవును సార్, వాళ్ళను యూట్యూబ్లో జాయిన్ అవ్వమని చెప్తున్నాం సార్. ఎందుకంటే ఇప్పుడు మన వాళ్ళు నలుగురు జాయిన్ అవ్వాలి సార్ స్పీకర్. అందుకే ఇబ్బంది అవుతుందని మేమే తీసేసినాం సార్. యూట్యూబ్లోకి వెళ్ళమని మెసేజ్ కూడా పెట్టినాం సార్ వాట్సాప్లో. కొంతమంది సార్ లిమిట్ ఇది. కొంతమంది అంటున్నాను సార్. అందుకే సార్ ఇప్పుడు యూట్యూబ్లోకి ఇచ్చేస్తాం సార్. మిగతా యూట్యూబ్లో కూడా సేమ్ లైవ్ పోతుంటుంది. అదే పెట్టినా సార్, లింక్ కూడా పెట్టాను వాళ్ళకు. అది ఎనాగల్ అయిపోయిన తర్వాత మళ్ళీ అలా చేస్తాం ఏదో ఒకటి అలర్జీ. Sir, good morning, sir. Sir, inaugural session కి join అయ్యాను, sir. Sir, inaugural session కి join అయ్యాను, sir. Sir. Hello. Sir. Hello.
హలో
Sir, ఇంటికి సార్ చెప్పండి సార్.
సార్ సిద్ధారెడ్డి సార్.
సార్
సార్ హేమచంద్రారెడ్డి స్పీకరా సార్?
కీనోట్ స్పీకర్ సార్.
కీనోట్ స్పీకర్, ఓకే. It is my have 30 years of teaching experience, out of which 17 years as a professor at JNTU. And some has received 3 prestigious awards such as Refrigeration and Best Teacher Award by the state government, and Broad Outlook Reader and Broad Outlook Learner Teacher Gold Award. Hello? సార్ అప్డేట్ చేసుకుంటారు. ఓకేనా సార్? ఓకేనా? హలో సార్, సిద్ధారెడ్డి సార్. హలో సార్, ఓకేనా?
సార్ మ్యూట్ చేసుకోండి మీద ఒకసారి.
ఓకే ఓకే. సార్ ఇక్కడ మ్యూట్ అనే ఉంది,
అక్కడ క్లిక్ చేయండి.
ఓకే ఓకే. మీరు చెప్పేది వినిపిస్తుంది ఇప్పుడు, వినిపించకూడదా? హలో
ఇంటికి వస్తుంది. ఆయనకి మీకు ఇద్దరికి పంపించినట్టున్నారు సార్. అవును సార్, అవును సార్, అవును సార్, అవును సార్. ఏం చంద్రాడు సార్ సార్ పంపించిన దేని గురించి కనుక్కోలేను, ఆయన పంపించిన అని చెప్పినా నేను. నాకు ఫోన్ చేయమని సిద్ధాడు.
అట్లనే అంతే చెప్పింది మన వీడియో.
సార్తో మాట్లాడినా, సార్కు లింక్ పంపించినావు కదా, సారు ఫోన్లోనే జాయిన్ అవుతాడంటలే, జర్నీలో ఉన్నాడంట. ఇప్పుడు రెడీ జాయిన్ అవుతాడు చూడు. సార్కు పంపించినావు, ఇద్దరు పంపించినావు కదా, పిఏకు ఆయనకి ఇద్దరికి. మీకు కూడా పంపించినాడు సార్ అని చెప్పిన, జాయిన్ అవుతాడు ఇప్పుడు ఫోన్లోంచి అన్నాడు. ఓకే రైట్.
క్లాస్
సార్ వాళ్ళు అన్మ్యూట్ చేయలేము. సార్ కూడా అన్మ్యూట్ చేసుకోండి. అయ్యానా
So no voice check it out. No voice check it out. No voice check it out.
హలో సార్, గుడ్ మార్నింగ్ సార్.
గుడ్ మార్నింగ్. గుడ్ మార్నింగ్ సార్. సార్ వచ్చినాడా?
సార్ వచ్చాడు సార్. స్పీకర్ ఆఫ్లో ఉంది సార్ సార్ది.
అవునా, నేను మెసేజ్ పెడతాను.
సార్ సార్ రామరెడ్డి సార్. సార్ సార్ హేమచంద్ర సార్, గుడ్ మార్నింగ్ సార్.
Good morning.
Sir, good morning, sir.
Good morning. Good morning, Tirupati Reddy. Good morning, JP sir.
Sir, good morning, sir. Good morning.
Good morning.
సార్ shall we start, sir?
Yes, please.
Good morning, sir.
So good morning to all of you. Myself, Dr. B. Siddhareddy, Associate Professor in Mechanical Engineering, and I am the coordinator of this Faculty Development Program. So it gives me an immense pleasure to welcome you all for the inaugural session of AICTE sponsored 2-week online FDP for phase 1 on renewable energy intervention in industry, commercial and domestic application. So first of all, I would like to thank today's keynote speaker, Professor K. Hemchandra Reddy Garu, Professor of Mechanical Engineering and Chairman, Andhra Pradesh State Council of Higher Education, our beloved Principal, Dr. T. Jayachandra Prasad Garu, Dean Admin and Director Placements, Dr. D.V. Ashok Kumar Garu, Dean Student Affairs, Dr. B. Ramreddy Garu, and Head of the Mechanical Engineering, Dr. K. Tirupati Reddy Garu. So invited speakers and participants for taking your time off from your busy schedules and making this spectacular morning with your glorious presence. So any activity, we require the blessings of Almighty. So now we begin the faculty development program with the virtual lighting of the So now I request Mr. Upendra, please play the sound.
సిమెంట్స్ వర్క్షాప్ 2 days.
తీసుకున్నాడా?
సుబ్రాజ్ సార్ ఉన్నాడు.
ఈరోజు రేపు
ఈ రోజు రేపు అటెండెన్స్ ఎలా చేయాలి సార్?
ఈరోజు అలా చేసుకోండి,
రెస్పెక్ట్ అవర్స్ అటెండెన్స్
చేసుకోవడం. మీకు అదే కదా మెసేజ్ పెట్టాను అంతకుముందు.
ఇంకొకటి సార్, ఇది మొన్న 18 to 24 వాళ్ళకి మొత్తం ఫైనల్ ఇయర్స్ అందరికి మనం పంపించాం.
అది మీరు వేసుకోవాల్సిన అవసరం లేదు. అది ఎక్కడ వస్తుంది
అంటే మాకు రిపోర్ట్ పెట్టమన్నారు కదా సార్,
అది తీసేయండి.
తీసేసి పెట్టాలి కదా సార్?
మీరు అది నోట్, మీకు అది నోట్ కాదు కదా.
Upendra. So thank you. So the objective of this faculty development program is to create awareness about the utilization of the renewable energy. So for industry, commercial and domestic applications like solar PV, solar power plants, solar dryers, windmill, wind energies, ocean energies and bioenergy, etc. And to build the confidence among the participants for the development of new renewable energy technologies, so that leads to the environmental sustainability. So by this program, so the faculty will gain the knowledge of renewable energy and transfers to the students community. So students community will get the new job opportunities in the renewable field by gaining the knowledge from the faculty. So hence it is very important to bring the awareness about the renewable energy, to do the research works and projects and to create the knowledge base. So towards these objectives, AICTE has recognized renewable energy technologies as one of the thrust area, and this FDP has sanctioned to the mechanical engineering department. So I must thank AICTE for sanctioning this faculty development program. So for this faculty development program, we had a huge response from the participants, about 560, not only from the mechanical engineering, even from the other engineering streams also registered for this FDP. And this FDP was planned with 24 lecture sessions and 3 virtual lab tours. So for this FDP, all the resource persons were drawn from reputed institutions like IITs, NITs, and also from the reputed research organizations like National Institute of Ocean Technology, National Institute of Wind Energy, and industries like SSV Energy and Infrastructure Private Limited, Senvian India Private Limited, Sun Energy Solar, and E-Tech Consultancy Services and Enterprises. So I thank all the distinguished speakers for accepting our invitation to deliver the expert talk for the sessions through online. So I wish all of us will have an insightful and fruitful sessions ahead. So with the ideas will lead to new implementable proposals. So with this, now I request Head of the Mechanical Engineering Department, so Dr. K. Tirupati Reddy Garu, to speak a few words on this occasion. So over to you, sir.
Thank you, sir. Thank you. Respected Chairman, Dr. M. Shantaramud Garu, our beloved MD, Mr. Sivaram Garu, our beloved Principal, Dr. M. T. Jason Prasad, Director, Placements, and Dr. D. V. Ashok Kumar, Dean Student Affairs, Dr. P. Ram Reddy Garu, and FDP Coordinator, Dr. B. Siddha Reddy, and today's chief guest of this AICTE sponsored FDP, Dr. K. Hemchandra Reddy Garu, Chairman, Andhra Pradesh State Council for Higher Education, and my dear participants of various engineering colleges. A warm welcome for this faculty development program organized by RGM College of Engineering and Technology, Department of Mechanical Engineering. Thank you for registering for this program. Hope this program will help you a lot in academically and researchably also. With this, I conclude myself, and I will invite Dr. Hemchandra Reddy Garu to speak few words on this occasion. Sir, please.
Very good morning to all of you. The chairman of the group of institutions, Shantaramud Garu, the managing director, Shivaram Garu, my good friend and principal of the college, Professor T. Jayachandra Prasad Garu, another friend, Tirupati Reddy Garu, HOD Mechanical Engineering, the coordinator, Siddha Reddy Garu, Ashok Kumar, and all other distinguished faculty members of this RGM, and the participants. Very good morning to all of you yet again. And at the outset, I take this opportunity to congratulate the RGM College of Engineering for organizing a wonderful workshop on a very pertinent topic. And I am also glad to know that AICTE has sponsored this program. This is much needed at this point of time because, world is talking about the energy security. India more so, being an emerging country, after food security, energy security is one thing that we all should be discussing, debating, and researching in educational institutions as well as the industries. For quite some time since I started understanding the economics of countries and the economics of the globe, India is labeled as a developing country, and we all expect it to be a developed nation. We all wanted to see India emerge as a developed nation. One thing we all should understand that status of development and economy are correlated to the energy consumption. Right now, the India's per capita energy consumption is quite low, at least 100 times lower than the most developed countries like the USA. So, when India starts moving from developing nation status to developed nation, quite obviously, every one of us can expect that energy consumption shall go up. And energy consumption is one of the parameters to decide the wealth of a country. Now, when that being the case, ever since we attained independence, we have added huge capacity in terms of energy, and Indian government has taken up a mission of energy for all, including electrification of the rural India completely. And in the pursuit, the government is successful, and we are in the process of producing enough power to meet the present day's demand. Having said this, the peak energy supply demand is close to 30%. This is the problem now India's major industries are facing today. And we need to produce the energy for today's needs as well as the future needs. And when I'm talking about future needs, consider the fact that India is growing and technologies are being embraced, and people are moving towards comfort. And to say air conditioner was once a luxury, today it is a necessity. And today we see almost every household, going for an air conditioner. So that obviously means the future energy demands would grow exponentially, and we should have a strategy to meet the future energy demands. Now, having said this, the energy demand was in the initial phases was typically met from hydel and thermal power stations, and we all know we have limitations with regard to hydel power generation. Close to 25% of the demand we can meet through hydel energy. And we all have seen a lot of multi-purpose projects coming in, and they are continuous to come. People are exploring the hydel energy, which is supposed to be a very clean source of energy. But then there is an upper cap, and you cannot go on increasing the energy production through hydel energy. And thermal energy, for obvious reasons, because all the participants also are fully aware that it has its own disadvantages. The addition of carbon dioxide into Earth's atmosphere is one serious concern. People link it to global warming, and they say carbon dioxide levels in the atmosphere as it is as on today is almost double the carbon dioxide levels as compared to the pre-industrial era. So that obviously means we are bringing out carbon from somewhere and converting that into carbon dioxide in the process of by involving in the process of combustion, and carbon dioxide is released. Now the question is twofold: how efficient the combustion could be, and as the combustion efficiency increases, the fuel calorific value could be harnessed as much as possible. So all efforts of the scientists and engineers all through was to improve the combustion efficiency. And combustion efficiency has been increased considerably, like we see, in whatever fashion, automobiles, other day we were giving, close to 6 kilometers per liter. Now we could achieve, Siddharthi, can you ask them to mute? Yeah, no problem. We don't know where it is. So the automobiles which were moving only hardly 6 kilometers per liter. Now today we see 24 kilometers per liter, a little more than that, which was seen to be quite impossible, and today it is made possible. All because of the technology improvement, research going on, and combustion efficiencies that we have achieved. And so is the case with the thermal power plants, where coal burning and efficiencies are considerably improved. Now, considerable increase in the efficiency of combustion can only result in reduced carbon dioxide emissions. But we cannot avoid releasing carbon dioxide because that is going to be a definite byproduct of this combustion. Now, when people say global warming is because of carbon dioxide and you cannot, contribute to carbon dioxide, now carbon credits have come into picture. And parallelly, what, the mindless activity we are all involved over a period of time is to release more carbon dioxide and cut trees, deforestation. Now, trees, we all know the photosynthesis reaction. Trees absorb carbon dioxide and then, they grow. But we are, going for two such activities of harming the Mother Earth. One is releasing carbon dioxide and the other is cutting the trees. And thereby, carbon dioxide is accumulating more and more in the atmosphere. Now, this is a serious concern. Now, people are talking about carbon credits. People are very particular about greenhouse gases. International level resolutions ask for 25% reduction in the carbon dioxide liberation. This is a very tough ask for all of us. Now, at this juncture, the non-conventional energies have come into forefront. And it's not a new topic as of now. For decades, we have been parallelly talking about the non-conventional energies or renewable energies. And we started harnessing solar energy, and solar energy was predominantly or fundamentally harnessed into thermal energy as well as photovoltaic energy. The primitive photovoltaic conversions were working at a very low efficiency of 6% or so. And today we could go up to 16, 17, and somewhere is claiming at 20%. So that is making the cost of solar photovoltaic installations very cheap. Now there is clearly a way out, and today, a state like Andhra Pradesh is planning for 10,000 megawatts of solar photovoltaic energy capacity addition. And not only this, the wind energy, particularly at favorable locations, people started harnessing, which is absolutely pollution-free. And, wind energy is being harnessed at favorable locations. Anantapur, of course, stands very tall in the state of Andhra Pradesh, in the map of Andhra Pradesh in wind energy. So we started moving in that direction. Technology is now very much available. Technology is evolved, and we are in a position to use that. Now there are again concerns like to meet 1/10 of the world's energy demand. Probably we need to forego 25% of the cropland. I have already told you that there is a food security, which is a major concern, feeding every human being on this globe. That should be the primary concern. Now, losing the cropland to produce non-conventional energies, in terms of solar installations, in terms of bio energies, it's always a tough ask. Then people started thinking of such bioenergies which can be produced in barren lands, rather uncultivable lands. So even this experiment is paving way. And in a nutshell, I should say technologies are very strongly emerging. And, today our job is to research more on this and bring it in a way that, at micro, macro level, we should be using the renewable energies. Renewable energies. Now, these renewable energies should be, harnessed more so at a micro level as well. Now, today's technologies are more or less for huge energy generation installations. And solar energy, we saw it very conveniently being used at the household as well. So therefore, we have a greater responsibility, in achieving the micro level technologies and make it acceptable to the consumer. And for some time, the cost of installations was a big worry, and return on investment was a big worry. And today, it is in the sight. Now, probably, I feel that energy security is not an impossible task for the world, and particularly using the non-conventional energy, renewable in nature, which are non-polluting in nature. Or we should go in a huge way, in order to change the complexion of this world and render the world safe to live for the next generations. So, at this, with this, a few remarks, I once again take this opportunity to congratulate RGM, for coming out with the faculty development program on a very pertinent topic. I'm sure, mechanical engineering department of RGM is doing a very good job. And I'm glad to know that, people from various other disciplines are also drawn into this workshop. Fundamentally, this renewable energy concept is interdisciplinary in nature. And today, NEP is also talking about interdisciplinary research. Now, cutting across the boundaries, cutting across the disciplines, we should come together. We should evolve new technologies. We should arrive at new solutions that can make the lives of the people very, very comfortable, and also render the globe very secure. So, thank you very much for the opportunity given. I wish this faculty development program a grand success. I'm glad you have drawn people from various industries and reputed organizations to deliver their lectures. And I have no doubt whatsoever that the participants will have a very rich learning experience participating in the faculty development program. So these days, virtual faculty development programs, virtual meetings are a quite common thing. But effectiveness is not at ascertained. Now, my appeal to all the participants: please glue to your computers. Be very attentive as though you are attending a physical faculty development workshop. And, you know very well that you are not being monitored. Now, as I am speaking, I am not really sure how many of you are attentive listening to me, and I really don't know what is the usefulness of my talk, this brief talk, but definitely my appeal to all the faculty development, the participants of this faculty development program: please be attentive and get the maximum benefit out of this workshop. Sir Jayachandra Prasad Garu, thank you for giving me this wonderful opportunity. And I was a little worried when Siddharth said I'm going to deliver a keynote address, and I got completely relieved when the HOD said, Tirupati Reddy said, asked me to speak a few words only. So I was quite relieved because I was not prepared for a keynote lecture. I thought I'm being invited there as a chief guest. So this is a chief guest. Please treat this as a chief guest message. And I wish all of you all the very best. Thanks for the opportunity.
Thank you, sir. Thank you very much, sir. Thanks for your blessings and wishes, sir.
Tirupati Reddy, my pleasure.
Thanks, sir.
Thank you, sir. Even in spite of your busy schedule, you attended, you have joined for this session, and you have given a wonderful information regarding the renewable energies. So, and enlightened our participants in this regard, sir. Thank you, sir, once again.
Pleasure. Sir, Principal Garu, I may be permitted to leave now.
Thank you, sir.
Wish you all the very best. Thank you.
Thank you, sir.
Madam.
So thanks to the management, Dr. M. Shantiramadu sir and Managing Director M. Sivaram sir and Principal of RGM set Dr. T. Ejector Prasad sir, Dean Admin and Director Placements Dr. D. V. Ashok Kumar sir and Dean Student Affairs Dr. B. Ramareddy sir and Head of the Mechanical Engineering Department Dr. K. Tirupati Reddy sir for joining this and making the program success. Thank you, sir. Thank you, one and all.
Thank you, Shivadi.
Thank you, sir.
Thank you.
Now I request Dr. V. Sivardi sir, please introduce the today's session. Sivardi sir.
सर आप ऑनलाइन में हैं सर?
Yeah. This is. So dear participants, so once again good morning to all of you and thanks for joining the inaugural session and making the.
तो सर आप लॉगिन कर दीजिए, आप जस्ट आपको जीमेल किया ना सर, मैंने आपको लिंक.
So we have the first session by Dr. S.C. Kaushik, Professor Center for Energy Studies at IIT Delhi. So sir is going to give a talk on solar cooling options. So before handovering the session to the Professor S.C. Kaushik sir, now I request Professor V. Sivardi. So please introduce the today's
ఉన్నాడా? ఏది కనపడలేదు, ఎక్కడుంది సార్? చూడు.
Hello.
Siddharth.
Hello, Dr. Reddy. I am audible.
Yes, yes, sir. You are audible, sir.
Yes. Okay, okay.
Yes, sir.
So,
sir, good morning, sir.
I can start.
Kaushik sir.
नहीं सर, just
Good morning.
Sir. So first of all, I would like to thank
PPT
for
ready, sir.
our invitation to give an expert talk on solar cooling options, sir, in the today's FDP program on renewable energy intervention in industry, commercial and domestic application. So I welcome you all, sir. Once again, I welcome you all. So today we have with us Dr. S.C. Kaushik, sir, Professor Center for Energy Studies at IIT Delhi. So sir is going to give an expert talk on solar cooling options. So now I request Professor V. Sivardi, please introduce the today's speaker, Dr. S.C. Kaushik, sir.
Thank you, sir. Good morning to all. Myself, Dr. V. Sivardi. On behalf of RGM College of Engineering and Technology, I am introducing. It's a great privilege for me क्योंकि मेरा गुरुजी को ही मैं introduce कर रहा हूँ. I'm introducing my guide, my philosopher. Professor S.C. Kaushik sir received his PhD in plasma science from IIT Delhi. After his PhD, his research field includes the activities in plasma science and thermal science and engineering, energy conversion and heat recovery, next solar refrigeration and air conditioning, solar architecture and thermal storage and power generation. I think I worked with sir in the last area, thermal storage and power generation. It's a great opportunity I got. And he has made significant contribution in the field of, as evidenced by his more than 400 research publications in reputed high impact factor SCI journals, not SCI, high impact factor SCI journals. Professor S.C. Kaushik has also completed several sponsored and consultancy projects from various government and private agencies. It is greatest news for us, especially he has guided more than 50 PhD students and 75 MTech projects. Professor S.C. Kaushik has authored several books of first kind. On that, some of the headings I am reading: Solar Refrigeration and Space Conditioning, Thermal Control in Passive Solar Buildings, Greenhouse Science Technology, Alternate Energy Sources, and Energy and Environmental Laboratory Experiments. Next, Alternatives in Refrigeration and Air Conditioning. Next, Finite Time Thermodynamics of Power and Refrigeration Cycles. Majority of the textbooks are available in Amazon also. Next, Professor S.C. Kaushik has been the postdoctoral fellow at Queensland University, Australia, and visiting professor at LES, IIM, UNAM, Mexico, and Madame Curie visiting fellow of European Commission, Paris, France. Next, his specific contributions on energy systems, he has been recognized by national and international awards. To his credit, Young Scientist UNESCO Award, Harihom Preet SS Bhatnagar Award, and Divya Jyoti Science and Technology Award. Professor S.C. Kaushik has a member of ISCS Australia and IIR France, and life member of various other professional sciences like CESI, IST, ISM, etc. And also he has been National Project Director cum Coordinator of MNRE sponsored Renewable Energy Fellow Programs from 2005 to 2010, and head Hindi Management Cell at IIT Delhi from 2005 to 2009. Next, Professor S.C. Kaushik has also been nominated as an expert member of advisory and selection boards of various organizations like ONGC Energy Center, Jeremy, MNRE, TERI, BE, BIS, BMTPC, NTPC, and CSR and DST. Why? Because in this area, solar concentration, especially when I am working with SAR, is ONGC and MNRE especially is an advisor for solar concentrated technologies. Next, Professor S.C. Kaushik has been popular with the top academic researcher performer, first rank holder on all India level in the subject area of energy for the last 5 to 10 research year publication, citation, and H-index based as per the Scopus data reported in NST, MIS, DST, Government of India, New Delhi. And I am happy to share you all that Professor S.C. Kaushik have been placed 1442 rank in the research area of energy in the world ranking of top 2 scientists published at Stanford University. These all are credits about SAR research area and SAR achievements. This every person, majority SAR knowing persons all are knows. But as a student, I know SAR as the holistic development of student, not career, personal career or jobs. Or this secondary, as a human being, how to live. The human, universal human values to the student community. He initiated at 1980s. The student, before joining his student, I am a 0 in this area. At the end of PhD, I am 1. Because without his guidance related to the trust to the love, he is the passionate to the student community. He expects from our students only one thing: as a human being, you have to live. You achieved, okay, top positions are not that secondary, but you are living like a human being. Why? Because I am insisting these points. From 2015 onwards, AACT recognized human values to the student community, but my guide is recognized at 1980s. It is proudly, sir. Now session is yours, sir.
Okay, thank you, Dr. Shiva Reddy, for the kind words. And I also thank the organizers and HOD Mechanical and Technology for giving me this opportunity to be with all faculty development program participants. I am happy that the main theme of the faculty development program is on renewable energy intervention in industry. Now, we know that renewable energy sources are now contributing for the overall energy capacity of the nation. And especially, you can say the renewable energy like solar, wind, biomass, they are the more prominent in addition to the hydroelectric, which is some indirect form of solar energy. So people have been bothering about the indirect sources of solar energy because solar energy is the ultimate source of energy. All other sources of energy are derived directly or indirectly from solar energy. So we worship sun as a god because it is the ultimate source of life as well as energy. So when we talk about renewable energy, solar energy has a prominent place and it plays a prominent role in the overall energy scenario. Am I audible? Yes. Is it okay?
Sir, you are audible.
Yes.
Audible, sir.
Yes, sir.
Okay, okay. If there is any problem, please tell me so that okay. So what I want to convey the message that renewable energy sources nowadays is not a new thing. Although people have been knowing renewable energy sources, especially solar energy, from the very beginning and utilizing solar energy for simple applications. But nowadays, solar energy is intervening in the industry because the technology, science and technology of solar energy has come to that stage that now it can be directly implemented and industries are coming up for this. Now, solar energy has many advantages. For example, it is ultimate source of energy. It is abundantly available. It is pollutionless source of energy. It is freely available everywhere. But at the same time, it has some problems for its technological utilization. The major drawbacks, or you can say major constraints for the utilization of solar energy is that it is dilute in nature. That is, so for collecting large amount of solar energy for any technological utilization, we need very high solar collection areas, or we need very highly efficient solar collectors. Second, you can say constraint in the utilization of solar energy is that it is intermittent in nature. It is available in daytime, not in the night time. It is time dependent. It is more available in summer, less in winter, and not available in monsoon season. So these are the two major drawbacks of solar energy, and that is why for any practical and technological utilization of solar energy, what we need is efficient solar collection and storage system. Whether these applications are, say, for power generation, for solar heating of water, so all these applications, whether it is for space heating, water heating, or solar drying, or solar power generation, all these applications are, you can say, prominent. But one of the most attractive application of solar energy is solar cooling. Now, why solar cooling is so attractive? The first point, first reason for this is that cooling is needed in hot regions. And cooling is needed when maximum solar energy is available. For example, in summer, the maximum solar energy is available at noon time. So maximum cooling is also needed at that time. So it is this matching, phase matching of the availability of the energy resource and the demand of cooling, because they are at the same time. So we can utilize maximum amount of solar energy for cooling purpose at that time. So it is one positive, one very attractive proposal. You can availability of the energy resource and the demand of cooling, they are in phase. Now, second point is that solar energy is needed in hotter regions. So maximum air conditioning is needed in hotter regions. So where maximum solar energy is available. So these are the 2 points which are very important. Now, the intermittent nature of solar energy, which is, you can say, because of the time dependence of solar energy, it is available in the daytime, not in the night time. So some kind of energy storage systems are needed. Now, for cooling, we may say that the storage requirements may be less, because when maximum, so storage is not required. But for example, for refrigeration, we need continuous refrigerator operation. So for that purpose, we may need some kind of storage as well. For air conditioning, we may not need that much amount of storage of solar energy. So solar energy for cooling is very attractive. Now, why only solar? Any other renewable energy source can also be used for cooling. But solar cooling is needed because most of our agriculture food production centers are located in remote rural areas, which are very far away. And there are many underdeveloped countries where source of electricity is not available. So if solar energy can be used to provide cooling in those areas, cold storage facilities can be developed. Now, cold storage facilities in those areas will be a boon, because otherwise the agriculture products or food products, they are to be transported from the rural. Some kind of cold storage facilities can be provided in those remote rural areas, then we may say that utilization of solar energy is in the perfect phase. So otherwise, if solar cooling facilities are not available in those areas, the food products, because efficient or the proper suitable utilization of cold storage facilities is not being made in those areas. Solar cooling can provide those cold storage facilities in those remote areas which are far away from the urban areas, where there is no source of electricity and lot of land space is available. So solar cooling systems on a large scale can be provided in those areas, which can supply cold storage facilities for the whole rural community in those places. Not only food storage, but you can say in some areas where life-saving medicines are to be stored. So simple refrigerators can be developed and can be provided in those, you can say, rural healthcare centers, where you can say life-saving medicines can be stored and many people's life can be saved. So these are the attractive options for solar cooling. Now, solar cooling is also, you can say, attractive as compared to solar heating applications. For example, heating mid or after. So heating demand is out of phase with the availability of solar energy. We may need hot water, you can say early hours in the morning, or you can say after midnight. So in hotels or restaurants, hot water can be provided in the form of a storage tank or so. But solar cooling is one application where you can say storage requirement is minimum. Yes.
Sir, can you share your PPT, sir?
Yes.
Can you share your PPT?
I will just start.
Okay,
Yes.
okay, sir.
Yes. I will just.
Sir, please maximize.
Yeah. Is it okay now?
Sir, please maximize, sir. Full screen mode.
This was just the introduction which I now for
అన్నీ ఒక దాంట్లో వేసుకుంటే కన్ఫ్యూజ్ అవుతావు. ఫస్ట్ రాముడి సార్కి ఇచ్చేసి ఇలాంటి కవర్లు వేసుకో. అవసరం లేదు, రెస్పెక్ట్ చేసినప్పుడు. ఫస్ట్ చైర్మన్ ఆఫీస్ కాడ ఇచ్చేసి సార్
It's okay. Yes. Yes. Is it visible?
Visible, sir. Now screen is not shared, sir.
Screen is not coming. Okay. Is it okay?
Okay, sir. Now it is okay, sir.
It's okay now. So it's
okay, sir. Okay, sir. Please, sir.
Next, change करो. मार्कर पे करो. उसमें लगाओ करो. इस स्क्रीन पे वहाँ पे शुरू करो. इतना बस Okay, so I have just given the brief introduction for solar cooling. Now, as the presentation is on solar cooling options, and I have also mentioned that the demand of energy consumption in buildings for space conditioning is increasing globally as well as in our country. So there is a need to reduce the conventional energy consumption by alternative energy sources. the use of solar energy for building space conditioning is desirable and increasing day by day, and various heating and cooling options are being explored and researched all over the world as well as in India. The scope of solar cooling is an attractive option, and hence this talk is focusing on solar cooling options for building space conditioning. Various alternative cooling options and their solar operations, their performance and cost-effectiveness is to be discussed in this presentation. Now, I need not emphasize, you can say the cooling options, you can say it may be refrigeration application or air conditioning, but what is important is that both these applications are very important, you can say, part of thermal science and engineering. And any kind of development based on solar energy utilization for refrigeration and air conditioning is highly desirable. Now, the applications of refrigeration for food preservation and cold storage and the storage of medicines and milk products is well known. And at the same time, the application of air conditioning for comfort air conditioning, for human comfort, industrial air conditioning, and control of temperature and humidity of air to perform a specific physical or chemical process is also desirable. Now, what are the basic cooling systems? You can say the conventional systems are based on vapor compression refrigeration. This system is called a mechanical refrigeration system, and here refrigerants are used to produce cooling effect. The cycle consists of a mechanical compressor, condenser, expansion device, and evaporator as main part of it. I think all mechanical engineers are familiar about it. Now, the other option is air cycle refrigeration, which is based on reversed Brayton cycle. And the third option is jet ejector cooling systems, which is also, you can say, based on evaporative cooling and jet ejector principle. And it uses some kind of thermo-compression process. But this is the kind of system is suitable only for industrial air conditioning. For other options are vapor absorption cooling system, which is similar to the vapor compression system, where mechanical compressor is replaced by a thermocompressor, which is nothing but a combination of heat exchangers, generator and absorber heat exchangers. And in addition to a refrigerant, we also use absorbent, a refrigerant combination as a working fluid. Other option is solar adsorption cooling, and which is also useful for desiccant cooling options for controlling the humidity as well. So it uses a desiccant material for surface absorption process and moisture removal from the air. The non-conventional cooling options include thermoelectric cooling, which is based on, you can say, Seebeck effect and Peltier effect, and system may use a thermoelectric generator based on Seebeck effect, and the reversed Seebeck effect is Peltier effect. The other options which are coming up are based on metal hydride refrigeration, which is also a solid adsorption type system, and thermoacoustic cooling option, which is the latest, you can say, development in the cooling options. And lastly, I would like to mention that to enhance the process of air conditioning, heat pipe based air conditioning systems are also being developed nowadays. Now, as I mentioned, that the scope of solar energy for cooling is very important, and that is why I have chosen this topic of solar cooling, because other solar energy applications are, you can say, very direct utilization of solar energy, because solar energy is available in the form of solar radiation, which can easily be converted into solar heat by a flat plate collector system, and heat can be utilized for heating applications directly. But solar cooling is based on utilizing the hotness of the sun for cooling. So how to achieve cooling from the hotness? That becomes a reversed phenomena. So some kind of thermodynamic systems are needed. Thermodynamic energy conversion cycles are needed. And that is why you can say the process of solar cooling is just more important and more, you can say, technologically difficult as well. Because for any thermodynamic conversion process, at each stage, some kind of loss in energy efficiency is there. So for solar cooling systems, overall efficiency becomes low as compared to solar heating systems. And as I mentioned that, especially when solar energy is to be used, the dilute and intermittent nature of solar energy is a major constraint. So we need a large solar collection area and more efficient energy storage system. Because solar cooling has a poor thermal efficiency because the thermodynamic conversion devices are involved. And presently, these systems are not cost effective because of these two constraints. So major research and development efforts on solar cooling systems is needed because solar cooling systems is having low efficiency and higher cost. And that is the only option which we have to explore. Now, as you can see from here, the time dependence of the availability of solar energy, the variation of the cooling and the heating demands. So cooling demand is in phase with the availability of the solar radiation, while heating demand is out of phase with the availability of the solar radiation. So we need some kind of storage for, you can say, heating, more storage options for heating, and even for, you can say, refrigeration process, as shown by the red portion, the storage requirement is to be made. Now, let us see how the solar cooling systems, you can say, market has grown right from the year 2004 to 2014, and now it is increasing. So the solar cooling demand and solar cooling systems in Europe and the other countries is increasing day by day. And the cost of these systems is coming down, as you can see, from the year 2005 to 2015. So we have that solar cooling systems are being developed all over the globe, but still we need more R&D efforts to be made for the solar cooling systems. You can see, according to the International Energy Agency Technology Roadmap, solar heating and cooling system share of the solar cooling system predicted values for even for the year 2050, as shown here. Similarly, final energy usage for the, you can say, renewable energy, especially solar heating and cooling, is increasing day by day. So let us now come to the basic, you can say, science and the basic options for utilizing solar energy for cooling. As I mentioned that we have conventional vapor compression cooling, then we have vapor absorption cooling, then we have vapor adsorption cooling, and then we have some non-conventional cooling options. Now, vapor compression refrigeration system, which is a, you can say, major part of the HVAC industry nowadays, about 70% of cooling demands are being met by the conventional vapor compression refrigeration systems. And it is, you can say, it is the major HVAC industry which is based on vapor compression refrigeration. But a stage has reached that these systems are not desirable. Why? Because these systems consume very large amount of energy. The power consumption, you can say, in our domestic sector is maximum for the refrigerator. For our office, maximum power consumption is for air conditioning. So because of the large amount of power consumption, which is high grade energy for these systems, so we have to look for alternative options, including solar, for operating these systems. So solar thermal conversion based vapor compression systems or photovoltaic based conversion systems, they are being, you can say, used for achieving this solar operation. Now, the vapor absorption systems. These are the, you can say, in addition to a refrigerant, absorbent is also used. So combination of refrigerant and absorbent is to be made, and choice of the working pairs to be used in vapor absorption system is a major problem. These systems can be, you can say, operated in the continuous mode or in the intermittent absorption mode. They can also be operated in the closed cycle mode or in the open cycle mode. Now, and closed cycle cooling systems can be used, and based on the solid adsorption process, metal hydride refrigeration systems are being developed nowadays. Now, other options, non-conventional cooling systems are like solar thermoelectric cooling, solar thermoacoustic cooling, and steam jet ejector cooling system as well. You can see that for operating the solar operated vapor compression systems, we have to use either Rankine cycle solar cooling or fuel assisted Rankine cycle or fuel assisted Brayton cycle. Steam jet ejector compression, which is steam jet ejector thermocompression based solar refrigeration system or solar cooling system, is suitable for air conditioning, industrial air conditioning, and a novel system based on gas cycle refrigeration, gas cycle compression solar refrigeration system is another option, which is based on Stirling cycle systems. Now, for vapor absorption systems, we may have open cycle absorption cooling or intermittent absorption cooling systems. And nowadays, the multi-effect absorption systems are also being developed. And based on the hybrid combinations, advanced absorption systems are being proposed. Now, vapor absorption cooling systems, you can say, which are suitable, closed cycle absorption systems or hybrid cooling systems. So we may, the classification of solar cooling systems can be made in this way. You can say heat driven, because solar energy is a heat driven option. Solar driven cooling systems, you can say closed cycle or open cycle system. They may be, you can say, liquid based or solid absorbent based, and then absorption chillers, liquid absorption or absorption based air conditioning options, which are known as the desiccant based cooling systems as well. Now, general, you can say, scheme of solar cooling system, that it consists of mainly 4 subsystems. Solar subsystem, which is here, solar subsystem, and then we have a storage option, and then we have chiller, and then we have application for the load. So this is just general scheme of solar cooling systems. Now, this is vapor compression refrigeration conventional. Now, what are the major, you can say, drawbacks for the conventional systems? Even from thermodynamic point of view, we have, you can say, dry or instead of wet compression in order to prevent damage to the reciprocating compression. So dry compression is desirable. If it is wet compression, then it may damage our reciprocating compression. Now, isentropic compression is replaced by throttling as work obtained is very low. Isobaric heat rejection in the condenser is possible. Now, major, you can say, drawbacks of vapor compression refrigeration system is that there, although it is a closed cycle system, but there may be some kind of leakage of the refrigerant. Initially, only, you can say, natural refrigerants like the carbon dioxide or you can say ammonia were being used, but later on some chlorofluorocarbon compounds, they were also suggested at the working combination, working fluids for the vapor compression system. But the problem is that if you look for the CFC based refrigerants, alternative refrigerants, then there is a possibility that if any CFC leakage is there, then it may cause the depletion of the ozone layer in the stratosphere. Now you may ask that why there is a leakage when it is a closed cycle. No doubt it is a closed cycle, But because the demand of the cooling systems is increasing day by day, so what happens that the rate at which these systems are being manufactured, the same rate that these systems are being abandoned. When these systems are being abandoned and left unattended, there is a possibility of leakage of the working fluid or CFC from these systems, and the chlorine which is leaking from these systems, it affects the ozone layer. There is ozone layer depletion in the stratosphere. So it is because of the depletion of the ozone layer, there is a possibility of the ultraviolet solar radiations coming through the ozone hole and reaching the Earth's surface, where it is very harmful for the human beings. It is very harmful for the skin and the eyes. So that is, you can say, not environmentally eco-friendly option. Another option is, you can say, these systems are consuming large amount of high-grade energy. And because the energy crisis is always there, so there is a shortage of to go for the conventional systems. But we have to look that whatever is available, we have to provide solar operation of these systems as well. So the refrigerants, you can say desirable refrigerants, which is needed in these systems, they, you can say, there are certain physical, chemical, and practical and thermodynamic requirements for these systems. So although we can meet these requirements for refrigerants, but from the environment point of view, as I mentioned, and from the energy requirement point of view, these refrigerants are not suitable. So we have to look for alternative refrigerants, and these are the alternative refrigerants which are, you can say, recommended. But with the alternative refrigerants, you can say the cooling capacity and the cooling COP achieved is not, you can say, very, very high. So we have to go for multiple effect or multi-stage vapor compression systems as well. So solar operation of these systems, if we want that our conventional system, which is dominating the HVAC industry, even now, you can say maximum market development in HVAC system is based on vapor compression cooling. So how to use solar energy for these systems? That is, either directly solar energy can be converted into solar energy, and then directly solar energy can be converted into electricity, and then can be used for vapor compression refrigeration system. Other option is that solar thermal electric conversion based vapor compression refrigeration can be achieved. Now, for the photovoltaic conversion based vapor compression refrigeration, we may use PV photovoltaic array which charges a battery and a DC motor which is coupled with the compressor. The success of the photovoltaic electric conversion based vapor compression refrigeration system will depend upon the performance and cost effective design of photovoltaic electric converter. So that these are the two options, you can say, which I have mentioned, solar thermal conversion based or photovoltaic. Now, photovoltaic conversion based is direct option. So now how the basic principle of the solar cell is there. It is just, you can say, available from the physics of photovoltaic energy conversion, and it makes use of the N-type semiconductor and P-type semiconductor, and there was a depletion zone in between them, and then we may convert solar energy into electrical energy. But as I mentioned, that the photovoltaic systems based vapor compression refrigeration depends upon the efficiency of the solar cell, and the efficiency of the solar cell is, you can say, low because of many factors. It is because of the reflection losses from the surface of the solar cell. All photons are not being utilized. Incomplete collection of electron hole pairs, incomplete absorption of photons, recombination of electron hole pairs which take place, and because of the many contact resistances which are involved. So what is needed is that the band gap of the, you can say, semiconductors which are to be used becomes an important, you can say, parameter for increasing the efficiency of the solar cells. As you can see from this figure, that the solar cell efficiency is depending upon the energy band gap, and there is optimum band gap at which the solar cell efficiency is maximum. Neither low band gap is desirable nor high band gap is desirable. As you can see that maximum, you can say, efficiency which can be claimed is for gallium arsenide and cadmium telluride, while commonly used material for solar cell development is silicon. So silicon, you can say, which has a energy band gap of around 1.1 electron volt, and for gallium arsenide it is about 1.4, and for cadmium telluride it is about 1.5. So these are the, you can say, silicon is the most commonly used working, you can say, material for the solar cell development, but efforts are being made nowadays for exploring new materials as well. So the overall view of a photovoltaic operated vapor compressor system is that a solar cell is to be, you can say, a module is to be made from different solar cells, and then a photovoltaic array, which is just, you can say, input energy source, and then we have different charge controller, battery and inverter, and then the DC load is, you can, or AC load, and we can convert, we can use the electricity for the vapor compression refrigeration system. So this is just a view of solar thermoelectric cooling option. How that the electricity obtained from the solar PV is being used, and we may have a solar thermoelectric cooling which is being operated by solar photovoltaic electricity. This is another, you can say, option which is common, which is coming up nowadays. Now, PV technology classification based on the different materials and different material technologies, say silicon crystalline technology or thin film technology, and then we also have amorphous silicon, copper, indium, and cadmium telluride, gallium arsenide, and multi-junction solar cells, as well as thin film solar cells are being developed nowadays. And you can say the cost of solar PV systems is also decreasing. And as the cost is decreasing, the usage of PV systems based solar cooling systems, you can say, is increasing. So solar thermal electric conversion based systems are based on, you can say, that solar radiation is to be converted into solar heat by using a solar collector system or concentrated solar collector systems, and then the receiver of the concentrated solar system, the energy can be transported and stored in the form of hot water or thermal energy storage, and then or some kind of alternative backup system can be provided, and the energy conversion system you can provide electrical energy which can be used in the conventional vapor compression system. So this is Rankine cycle based solar cooling system, which is using a parabolic trough collector system, and then a boiler heat exchanger, turbine, and then you can say electricity is being generated from the turbine, and then which can be used as input for the vapor compression system. But the problem for the solar thermal system is that we need many efficiency parameters. Like first, the efficiency of a solar collector is involved, then efficiency of a transport, efficiency of heat storage, efficiency of the heat engine, and efficiency of the generator, and then COP of the vapor compression system. Overall, you can say the efficiency becomes low. But because the solar collector system efficiency and the engine efficiency are depending upon the operating temperature. So as the operating temperature increases, the efficiency of the solar collector system decreases because the heat losses increases. So efficiency of the solar collector system is decreasing. But as the operating temperature increases, the efficiency of the heat engine, because the higher is the heat source temperature, higher is the efficiency of the heat engine. So we have, you can say, two contrasting systems which are being coupled. That solar collector system is being coupled with the solar heat engine, and then overall efficiency will be maximum at some optimum operating temperature. So obtaining this optimum operating temperature for a solar collection system, for a solar thermal system is desirable. So you can see here that solar collector efficiency is proportional to the difference in the temperature, while engine efficiency is, you can say, increasing as the operating temperature is increasing. So overall, we have the optimum operating temperature as the square root of the stagnation temperature and the ambient temperature, where stagnation temperature is the maximum collection temperature under no load condition. So this is the Rankine cycle solar cooling system, which is, you can say, as you can see, that solar collector loop is there, then heat engine loop is there, and then vapor compression system. So solar collector will provide heat from the solar this collection subsystem to the boiler of the heat engine, and then this heat engine, which is, you can say, Rankine cycle heat engine, the turbine output is being coupled with the compressor input. So the input energy for the compressor is being provided directly by the turbine, and then the vapor compression refrigeration system can work. And the most, you can say, conventionally R12, R22 and R11 were being used, but the alternative options, you can say, for the this heat engine part, R113 and R114. Nowadays, these old refrigerants have been replaced by new alternative refrigerants. But the desirable characteristic for the choice of the working fluid for the heat engine is that, as we can see from this temperature entropy diagram of different working fluids, for which you can say one option is for which the ds by dt is less than 0, S is the entropy, or ds by dt is equal to 0, or ds by dt is greater than 0. T is temperature. So you can see that for desirable, you can say, working fluid combinations, the last option, that when ds by dt is greater than 0, is the suitable option. Now we may have a single fluid Rankine cycle solar cooling system, or we may have a, you can say, double fluid. So if we have a same working fluid in the heat engine and the vapor compression part, we may have reduce the number of components. We may have a common condenser for these two options, and we can even integrate the solar collector with the boiler heat exchanger here. So we may have a very compact system, single fluid Rankine cycle cooling system, but overall efficiency of a single fluid Rankine cycle cooling system will be low as compared to a dual fluid system. Now, alternatively, we may provide some fuel assistance or fuel assisted regenerative Rankine cycle and power cooling option. You can see that here we may provide some regenerator here and a economizer heat exchanger and a superheater, just to increase the heat engine efficiency. And here this economizer will reduce the input energy requirement from the solar collection system. So you can say the sensible heat can be provided by the flat plate collector system, which can be reduced by providing this, you can say, economizer as well as this regenerator. So if this regenerator and this superheater will provide a higher inlet turbine temperature, so overall efficiency can be improved. So advantage of fuel assisted Rankine or Brayton cycle power cooling system can be that the working fluid can be adjusted and half solar collector area is required. Overall efficiency is improved, and the organic fluid suffers from the instabilities at higher temperature. So we may use low operating temperature working fluid as well. Now this is another option. You can say fuel assisted Brayton cycle And it makes use of the advantage of the Rankine cycle as well as the Brayton cycle. How? Because if we are using a steam as a working fluid in a Brayton cycle, and it means it is just combination of the Rankine cycle cooling option as well as the Brayton cycle cooling option. And overall, the efficiency is improved and we can provide cooling, but it is suitable for low, you can say overall COP is low, but the operating temperatures are low and we have to provide many components which are, you can say, just increasing the complexity in the cycle operation. So let us now say, as I mentioned, that for operating the conventional systems, we have either we have to go for the alternative refrigerants or we have to provide alternative cooling technologies. Now, alternative refrigerants is desirable because of the leakage of the CFCs which are causing environmental problems. High grade energy consumption, choice of the refrigerants to be made from the point of view of energy consumption as well as from the environment, eco-friendly environment. So these are the options. Another, you can say, gas compression cycle solar cooling system is has been proposed in the literature, and which is based on the two Stirling cycles. One is the Stirling heat engine providing virtual work input for the Stirling heat pump, and thereby using, say, the solar collection system here, solar collection system which may provide high temperature as well. So, for example, if a concentrating system is there, then we may provide, you can say, high temperature heat input for this Stirling cycle heat engine. And in this way, we can increase the COP of the Stirling refrigerator here. The advantage is that we need not provide any other option. High temperature concentrating solar collectors can provide high cooling capacity in these systems. But this system has been only developed, you can say, at in the laboratory. No commercial or industrial development of this is possible. Overall COP of the system, it is just Stirling heat engine, ideal case, and it is just the refrigeration case. So we have this option, but it is still being studied. Now, as I mentioned, that steam jet ejector cooling system is also another option where we are replacing the mechanical compressor by ejector compression system. It is some kind of thermocompression. Some kind of thermocompression is there. You can say it is a converging diverging nozzle, where you can say at the inlet nozzle is there and at the outlet we have some diffuser. Diffuser is behaving like a compressor and this nozzle is behaving like an expander. So by providing this, you can say we may have some heat engine coupled with the vapor compression cycle, say evaporator, condenser, expansion valve, and this compressor. So the overall efficiency is okay, but still we can say that this system is simple in design as compared to Rankine cycle cooling system. So it is jet ejector is the main part of the refrigeration cycle, and evaporative cooling principle is being used in this jet ejector cooling system. What is this evaporative cooling system? That if we have an earthen pot or a desert cooler where you can say water is being evaporated, when water is being evaporated, the latent heat of vaporization comes from the remaining water. And that is how the evaporator chamber of the cooling system is working in a jet ejector cooling system. So we are making use of the evaporative cooling option, as well as we are making use of the ejector compression, and overall system is simple in design as compared to a mechanical compression. In a mechanical compression, the 70% cost of the system is because of the compression. Here, the cost of the ejector compression is very low. So that is how this system is very much desirable for industrial air conditioning options. So as you can see that how the, you can say, latent heat of vaporization and the temperature drops of the remaining water, it can be simple calculated by the heat balance equation. So if 1 kilogram of water is evaporated, then 540 kilogram of water can be cooled by 1 degree centigrade. Alternatively, we can say that 1% of water is evaporated. If 1% of water is evaporated from the surface of the water, then remaining water can be cooled by 5.5 degrees centigrade. So it is, you can say, based on this principle that the ejector refrigeration system is using this principle in the evaporative cooling chamber of the system. So this system is simple in design and you can say viable. Overall COP, you can say, is also high because the input heat source temperature can be, you can say, it can be increased, and the common condenser temperature, common sink temperature can be used for the ejector cooling system. Now we come to the, you can say, vapor. What are the major, you can say, advantages of this? That the system is free from vibration and no moving part is involved, high reliability and have low maintenance, low cost and simple design, no refrigerant in case of steam, utilization of low grade heat like solar with refrigerant or exhaust, or steam of other processes can be utilized. But the major problem, you can say, drawback is low COP and large, enormous volume is to be handled of the vapor phase, high operating vacuum with the water, and only air conditioning can be achieved and low cooling capacity can be achieved. So we have to go for the vapor absorption refrigeration system. Now let me tell you why vapor absorption refrigeration system. Yes, before I start, I would like to know from the organizers, Dr. Hello.
Sir, please, sir.
I am audible?
Yes, sir.
Yes.
Yes, audible, sir.
Everything is moving fine?
Yeah, fine, sir.
Okay, okay. So now I go to the vapor absorption refrigeration part, which is the very, you can say, system. We compress the vapor phase of the refrigerant. And because the specific volume of the vapor phase is much larger, is about 100 times more than the liquid phase, so compression work required in a vapor compression system is much higher. And that is why the capacity of the mechanical compression is to be increased. Now, in vapor absorption system, what we do, the refrigerant vapor coming from the evaporator is dissolved in some absorbent solution so that it is converted into liquid phase. As you can see here, that the combination of refrigerant and absorbent, it is heated here with the help of the input energy, say solar energy, and then refrigerant vapor goes out, and then it is being condensed here in the vessel 2. So based on vessel 1 and vessel 2, the basic vapor absorption process can be understood. Vapor being produced here from the solution of the refrigerant and absorbent, and then this vapor phase is coming to the another heat exchanger or vessel 2 where it is being condensed because it comes in contact with the surrounding at a lower temperature. So it is converted into liquid phase. So this condensed liquid. Now in the daytime, in the night time, what we can do, that this liquid can be evaporated. So this basic principle of absorption of the refrigerant vapor in the absorbent solution is used in the intermittent vapor absorption system. But the process is the same for the open cycle as well as for the closed cycle as well as for the intermittent system as well. So this is the simple vapor absorption system. You can say condenser, expansion valve, and evaporator. These are the same as in a vapor compression system. the mechanical compressor is replaced by this generator absorber assembly. They are being replaced by this generator absorber assembly, and the purpose is to reduce the compression work. So what we do, that the vapor which is coming from the evaporator of absorbent is taken, and then it is being pumped with this liquid pump to the generator heat exchanger, where input and refrigerant vapor is generated, which is condensed in the condenser heat exchanger, and then condensate is passed through the expansion wall, and same process as in a vapor compression system. This is the only difference, that generator and absorber assembly is just replacing the mechanical compressor. So the overall COP of the vapor absorption cooling system is just based on the heat engine efficiency of the generator absorber assembly, and the vapor compression part is just, you can say, the between the condenser and the evaporator. If we make use of this common temperature, sink temperature for the condenser and absorber, then we have, you can say, this overall ideal efficiency of the vapor absorption system. So you can see that as compared to vapor compression cooling system, this heat engine efficiency is involved, which is much less than 1. So overall COP of vapor absorption system is less than the efficient than the COP of the vapor compression system. But that can be understood. Used in a vapor compression system is a high grade energy, while in a vapor absorption system, the input energy to be used is thermal energy, like low grade energy. So if we take into account the conversion of the high grade energy into low grade energy, then this, you can say, overall efficiency or overall COP of the vapor absorption system is comparable with the COP of the vapor compression system as well. So it is this efficiency factor which is coming up. Now, it just, you can say, cooling effect upon the input heat supply, which can be expressed as the mass of the refrigerant into latent heat of vaporization at the evaporator upon the total heat supply to the generator, which is used to heat the vapor from, you can say, liquid form to the vapor phase, and then when the vapor phase is evolved, this is the latent heat of vaporization which is involved. So if we just express it in terms of this recirculation ratio RR, which is MW by MR, and where MS is the total mass flow rate, and this is weak solution flow rate, and this is the refrigerant flow rate. So we have this simple expression, and we can see that delta H, which is nothing but the heat of dilution. Depending upon the heat of dilution, we can say that the COP of the actual COP would be less than 1, it would be equal to 1, or it would be more than 1. So if delta H is 0, which is the case for ideal solution, then we have, you can say, the COP, ideal COP of the vapor absorption system would be unity. If delta H is positive, heat of dilution is positive. It depends upon whether the absorption process in the absorber is exothermic or endothermic. If it is exothermic, then it is positive. If it is endothermic, then you can say, depending upon whether this delta H is positive or negative. If it is positive, then you can see that COP actual would be less than 1. If delta H is negative, then you can see that the COP actual would be more than 1. So which is desirable. So we have this choice of the refrigerant and absorbent which is to be made. It depends upon whether this delta H is negative. And other characteristics which are desirable for the choice of the refrigerant and absorbent pairs are as mentioned here. That there must be high solubility of the refrigerant in the absorbent, large boiling point difference between the refrigerant and the absorbent, low viscosity to reduce the pump work, low freezing point, and good chemical and thermal stability requirements are there. Practically, cost should be low, availability should be high, the refrigerant should be non-toxic and non-flammable. Heat of dilution is 0 or it should be negative. So delta H should be negative. It is desirable. We have seen that if delta H is negative, only then COP actual is greater than 1. Absence of solid phase, you can say solid form during any part of the system, it will shut down the system so as well. So based on these, you can say conditions, the possible refrigerant absorbent combinations are that when water is being used as the refrigerant, the suitable absorbents are triethyl glycol, lithium bromide, lithium chloride, but with these combinations or multiple salt solutions, we have the problem of crystallization of the salt. So we have to avoid the use of lithium bromide salt for wide range of operating conditions. But water and lithium bromide combination is the most commonly used. Another combination is that when ammonia is being used as a refrigerant, the possible absorbents are water, calcium chloride, sodium thiocyanate, lithium bromide, and lithium nitrate. Now, ammonia water is the most common and oldest working fluid combinations for the vapor absorption refrigeration systems. But the difference between the ammonia and the water, it means the boiling point of ammonia and water, they differ by a smaller amount as compared to water and lithium bromide combination. So there is a possibility of water vapors being associated with the ammonia vapors, because the affinity of the water vapors with ammonia is strong as compared to the affinity between the lithium bromide and the water vapors. So we have a problem of the separation of the water vapors from the ammonia vapors, and that is why we need some kind of rectifier in a vapor absorption system in case ammonia water is being used as a working fluid combination. Now, another options which we have explored at IIT Delhi is alcohols, methanol or ethanol as a refrigerant, and then salt mixtures like lithium bromide, lithium chloride, zinc bromide, and multiple component salt mixtures which can be used as absorbents. So we have the you can say we have the disadvantage in ammonia water case or ammonia as refrigerant with suitable absorbents that high operating pressures are needed. While in case of water lithium bromide combination, low operating pressures are desirable, and even vacuum is to be created for the low pressure side. So alternatively, some phenols can be used as refrigerants and dimethyl chloride and diethyl chloride, but they may avoid the problems of ODP and GWP. But as you can say, ozone depletion potential and global warming potential, but still you can say for large capacity applications these are not suitable. Most commonly used refrigerant absorbent pairs are based on ammonia water and water lithium, which are commercially available vapor absorption systems. In India, Thermex is, you can say, manufacturing the vapor absorption systems based on these combinations as well. So we have, you can say, now a comparison of these two combinations, ammonia water or water lithium, a very, you can say, because these are the two options which are most suitable for vapor absorption systems, then we have to see that what are their relative merits and demerits. In ammonia water case, you can say the ammonia is refrigerant and water is absorbent. While in water lithium bromide case, water is the refrigerant and lithium bromide is the absorbent. Now here we have a high operating pressures. Nearly, you can say high pressure is 20 bar and low pressure is about 3 bar. Both are above atmospheric pressure. So we have the problem of high pressure vessels. Now, in case of water lithium bromide, we have low operating pressures, nearly you can say 30 millimeter of Hg and 6 millimeter of Hg. It is the high pressure side and it is the low pressure side. Both are, you can say, much lower than the atmospheric pressure, which is 760 millimeter of Hg. So we have a problem of the creating vacuum in case of water lithium bromide, and we have a problem of maintaining high pressure, high operating pressure vessels for the ammonia water case. Now, but ammonia water case is very much suitable for refrigeration as well as air conditioning, as well as heat pump operation. So that is the advantage of the ammonia. But while water lithium bromide is suitable only for air conditioning, because we cannot water is the refrigerant, we cannot go below 5 degrees centigrade. You can get all water conditions as compared to water lithium bromide, where lower generator temperature is desirable. Another advantage is that for ammonia water case, we may cool the condenser and the absorber either by water cooling or air cooling, water cooling from the cooling tower or air cooling from the ambient. But in case of water lithium bromide, only water cooling is desirable. Air cooling cannot operate the system for a longer time. Now here we need analyzer and rectifier to separate the water vapors from the ammonia vapors because of high affinity between the water vapor and ammonia vapor and low boiling point difference. Now in case of this, this requirement of rectification is not needed because the temperature, boiling point temperature difference is also very large. In case of ammonia water, there is no problem of crystallization. But in case of water lithium bromide, because lithium bromide is a solid, at lower pressure, where you can say, and lower temperature, there is a problem of crystallization. So there is a problem of choking of the system operation due to the crystallization of the lithium bromide during system operation. Now, because the water vapors are associated with the ammonia vapors, so cooling capacity is lower. So COP is also lower. It is 0.5 to 0.6 for normal operating conditions, while it is 0.7 to 0.8 or even higher for water lithium bromide case. Now, for ammonia water, it is low cost and easily available. But for water lithium bromide, the cost of the lithium bromide is high, and you can say it is toxic, and while it is non-toxic, it may be a health hazard, chemically unstable, and it may be corrosive. So these are the you can say comparative this one. Now for water lithium bromide, you can say what is needed is how to, you can say, thermally design this system. You can say for a solar operation, solar collector is supplying heat to the generator in the range 80 to 90 degrees centigrade, and the evaporator is being operated 5 to 10 degrees centigrade. The condenser and the absorber are being operated, say, from 30 degree to 40 degrees centigrade. And we have two, you can say, pressure level, high side pressure above this condenser and the generator, and low side pressure is in the absorber and the evaporator. So there is this portion at state point 6, there is a problem of crystallization for water lithium bromide because the pressure is reduced, temperature is low, so lithium bromide crystallization. And the limit is that when the absorbent concentration is reaching 0.635, then there is a problem of crystallization. So we have to maintain the system operation in such a way, or the operating conditions in such a way, that this concentration of the solution is never more than 0.63. If it is more, then there is a problem of crystallization here. So next is that ammonia water case. For ammonia water cycle, we have, you can say, condenser and evaporator and absorber is same, but for the generator, because along with the water vapors, some ammonia vapors, water vapors are also evolved. So what we use a rectifier, which is nothing but a fractionating distillation column, which can condense the water vapors through this, you can say, analyzer, and the water vapors after being condensed goes back to the generator, and with the perfect design of the rectifier or this fractionating distillation column, which is known as analyzer, it is not 100% possible to separate the water vapor from the ammonia vapor. Even 1% or 1.5% or 0.5% water vapors are always associated with the ammonia vapors. So we cannot have a 100% concentration of the refrigerant here, ammonia. We will have 0.99 or 0.98 ammonia concentration. And even with that low water vapor concentration with the ammonia vapors, the condensation and the evaporation process are not perfect. So the cooling effect in the condenser is low. And that is why the COP of the ammonia water case is low as compared to the water lithium bromide case. Pressure levels are higher in case of ammonia vapors, but the advantage is because we can operate the evaporator for a wide range of operating conditions, not only -5 to -10, we can go even -22, say +20 degrees for the evaporator, and we can operate the, you can say, but it may not be a perfect rectification, but it is still working very well, even with 0.99 refrigerant concentration here. So ammonia water cycle as well as water lithium bromide cycle, these are the two options which you can say possible for the now. But the problem is that even with this single cycle like this one, whether it is water lithium bromide or ammonia water cycle, COP use COP to provide more cooling capacity in the evaporator. We need high collection area here for the, you can say, for providing heat input to the generator. And even for absorption, water lithium bromide or ammonia water system is low, which may not be suitable for any commercial or high technological application of these systems. So what we need is that to improve the COP of the vapor absorption system, we have to use a double effect water lithium bromide combination. What is double effect generation vapor absorption system? That between the generator and the condenser, we provide an additional heat exchanger. This is the additional heat exchanger between the generator one and the condenser. And the purpose of this condenser is that whatever is the solution which is left behind in the generator, it is reduced in temperature as well as in pressure, and then it is sent to this heat exchanger, where the vapor generated from this generator one are being condensed. So that heat of condensation is available for heating this solution in the generator two, and thereby more refrigerant vapor can be generated at this stage. So we have two-stage refrigerant vapor generation. First stage refrigerant vapor generation, and then second stage vapor generation. And this, then the left behind solution is again, you can say, and then it is passed through this expansion valve, reduced in pressure, and then it goes to the absorber. While this vapor reduced in pressure, then it is being condensed here. So it is being mixed with this condensate of this second stage refrigerant liquid. So after mixing in this condenser, it is being passed through this expansion valve and then evaporated. Now you can see that just by providing this one intermediate heat exchanger, between the generator and the condenser of the system, we have the cooling being produced in the evaporator is nearly twice. Why? Because first stage refrigerant vapor generation is this one, and second stage refrigerant vapor generation is this one. So the amount of refrigerant vapor which is condensed in the condenser is nearly twice as compared to the single stage system. So when it is, you can say twice, so the cooling capacity provided in the evaporator is also nearly twice. So the COP, with the same heat input, we are able to increase the refrigerant vapor generation as well as the cooling effect in the evaporator nearly twice. So COP is also nearly twice in the case of double effect generation water lithium bromide system. So the system is very effective, but you can see that we have now three operating pressures. One is the pressure in the absorber and the evaporator. Another is the pressure in the condenser and this generator 2. Another is the pressure in the generator 1. So three pressures are there: high side pressure, intermediate pressure, and then low side pressure. So, but just by providing this heat exchanger and this simple solution heat exchanger here we have two heat exchangers, but in a single state we have only one. So just by providing heat exchanger, and the cost of the heat exchanger is not much. So no additional cost, but the system can provide the COP nearly twice as compared to the single stage system. But at the same time, you can say the operating pressure in the generator 1 is excessively high. So we cannot use ammonia water as a working fluid for double effect system. Only water lithium bromide can be used for the double effect vapor absorption system, where operating pressures are much lower than the atmospheric pressure. So we don't need you can say high pressure vessels. So by providing double effect, similarly by providing triple effect generation, we can further increase the COP of the system. So by providing multi-stage, multi-effect generation, commercial vapor absorption unit with a higher COP and solar energy operation of that system is possible. Suzuki, not Suzuki, that this Japanese firm, one Japanese firm is there, which is commercially making these single effect, double effect, and the triple effect vapor absorption systems for the operation of these systems by using solar energy and by providing COP nearly twice or thrice of the single stage or single effect cycles. So it's a very, you can say, promising option. This is the triple effect absorption chiller. You can see at first stage, then second stage, and then third stage. Same principle as we have used for the double effect. Similarly here, the triple effect, and we can provide COP, higher COP, you can say nearly thrice as compared to the single stage system. Now, for solar cooling applications, this you can say hybrid cycle. This is a vapor absorption system. It is being coupled with a ejector cooling system, and it is being coupled with a vapor compression cooling system as well. So hybrid cycles, these are the, you can say, new cycles, advanced absorption cycles. We may have advanced absorption cycles in this vapor absorption system. We may have this heat engine part. This is the, or you can say the, we may have a cooling system based on steam that ejector or ejector compression refrigeration system, and then we may have this vapor compression system. So these hybrid cycles based solar cooling options are also being you can say tried and explored for the vapor absorption systems. Now let us just you can say what are the major advantages of the vapor absorption systems as compared to the vapor compression systems. You can just go to very low moving part, lower maintenance, lower energy and running cost, can operate on waste heat, lower evaporation temperature, less pump work, less chances of leakage of refrigeration. The performance of the system is not affected by load variation, and these systems are eco-friendly. For solar cooling systems, vapor absorption systems operated with solar energy is the best option. But still we may have the drawbacks, like initial cost becomes 15 to 20% higher because of the solar operation, and space requirement is also more, COP is less, and need more time to achieve a desired temperature. High energy, nearly 1.5 times more the cooling effect supply, and as compared to 1.2 to 1.3 times the vapor compression. So these are the vapor absorption systems. Now, for operating these systems in the continuous operation mode or in the intermittent system mode, you can say for the continuous operation, we may have the some kind of storage which is to be provided, and this storage can be provided in the form of hot water storage between the collector and the generator, or cold water storage as chilled water storage for producing excess cooling, or we may have to provide refrigerant storage after the condenser and the absorber within the vapor absorption cycle, or we may use a combination of all these, or some kind of storage with the help of auxiliary heat source, say biomass heat source or biogas heat source or electrical energy source can be provided to provide the storage for achieving the continuous operation of the vapor absorption system. Now, these systems can also be operated in the open cycle mode. Open cycle systems, you can say, we will discuss just the next option, but here I would like to mention that for the continuous operation of closed cycle systems, single effect, double effect, two-stage, triple effect, or multi-stage systems can be there. So continuous operation, 24 hours operation with the help of solar energy is possible with the help of this single effect, double effect, or triple effect cycles. And we may have to provide, you can see these are the storage options or auxiliary heat source. Now, the difference between the closed cycle and open cycle. For a closed cycle system, the system is exchanging only heat and work with the surroundings. But for open cycle systems, where you can say not only heat and work exchange with the surroundings, but even the mass exchange of the working fluid with the surroundings also takes place. So if mass exchange because the working fluid is ammonia or any other working fluid, and if it is, you can say, being exchanged with the atmosphere, it is not desirable, it is health hazard. So necessarily, we have to use water as a refrigerant in open cycle vapor absorption system. So these open cycle vapor absorption systems are suitable to provide air conditioning and most suitable for providing solar air conditioning. Now, this is the basic principle of the open cycle vapor absorption solar cooling system, that we have, you can say, the number of components are also reduced. We may eliminate the presence of the condenser. So we may need only solar, you can say, a collector generator to provide input heat, you can say, for regeneration. But what we actually have a absorber evaporator vessel, combined vessel for the absorption process and for the evaporation process, having a partition between them. Both are working at the low pressure, which is being maintained with the help of the vacuum pump. So it is a low pressure vessel where water is being sprayed here. Now water is being sprayed, and this latent heat of vaporization will come from the air which is to be cooled. This is the load. So the water being sprayed, when it is being sprayed, it is vaporizing. So because of the heat, sensible heat, which is, you can say, room air is being circulated. So unvaporized water is being collected here, and then it is again pumped to the makeup water. So this is the evaporator chamber. Now the water vapors which is generated is going to the absorber chamber, where solution of the refrigerant, say water lithium bromide or water lithium chloride or water calcium chloride, is being sprayed. Now that solution has a tendency to absorb this water vapor. So it will absorb this water vapor. It will become dilute in the absorbent and it will become rich in the water. So it is being collected here, and because the absorption process, heat would be rejected, that is being removed by the cooling tower. Simple cooling tower, or just by circulating water for cooling this solution. Now this solution, which is rich in the refrigerant or water, is being preheated through this heat exchanger, and then it is being sprayed through the solar energy is being supplied just by exposing this solution to the solar energy, and water will be evaporated from this conductor regenerator system, and then you can say concentrated absorbent solution is being received in the receiver, and that is being passed through the solution heat exchanger, which is rich in absorbent, and now it is being sprayed here, and it will absorb the water vapors coming from the here. So you can say the rate of water vapor evaporation in the collector regenerator system is same as the rate of water vapors which is being produced here. Water vapors
Sir, sorry, sir.
Sir.
Sir, there is no audio.
Is it okay now?
Sir, getting, sir, audio getting.
Audio, is it okay?
PPT is also visible, audio is getting, okay, sir.
And screen is also there?
Okay, sir, okay, sir.
Okay. I can continue?
Yeah, continue, sir.
Okay. So you can say this is the open cycle. This is the open cycle system. Here you can say this. The advantage of this is that rate of water mass evaporation here is same as the rate of water mass evaporation here. So just by, you can say, larger is the rate of water mass evaporation here, more will be the capacity of water vapors being generated here and being absorbed in the absorber. So the capacity of cooling capacity of the system can be increased by providing better design of the solar collector regenerator. Now, this based on this system, you can say a building is being cooled in Moscow. I have visited that place where building roof is being used as the solar collector regenerator, and this absorber evaporator assembly was installed in the wall. The interior of the wall is coupled with this evaporator, and the exterior of the wall was this absorber chamber. So it is being cooled by the cooling tower. So the building is being cooled through this evaporator coil, and with this cooling tower is connected with the absorber. And the roof of the building was acting as a solar collector regenerator. So this system is most suitable for providing large scale solar cooling option. Large scale solar cooling option can be provided by using this open cycle vapor absorption cooling. Now, because water is being lost to the ambient, so necessarily water is being used as a refrigerant. No other working fluid combination can be used. All other working fluid combinations like ammonia or carbon dioxide or any CFC, they may not be eco-friendly. So water lithium chloride is used in open cycle, and which is very cheaper than a lithium bromide combination. And water lithium bromide or water salt mixtures can be used as Is it okay? Why?
Sir, okay, sir. Okay, sir.
Why it is changing the mode? I don't know. Anyway, now you can say for improving the cooling capacity in COP, different designs of solar collector regenerator. One is the O-proof surface. I mentioned that for a building, but it is suitable for hot and dry climate because maximum rate of water mass evaporation can take place in hot and dry climate. But in a dusty, rainy season, it is contaminated. So another option is that we have a glazed solar collector regenerator. It will protect from dust, and we may provide a natural airflow to increase the rate of water evaporation. Or alternatively, we may provide a forced flow solar collector regenerator. It is suitable for very humid climate. Another option is that a solar still collector cum regenerator can be provided, where this collector regenerator is just like a solar still, and that can, you can say, control the humidity also. But because the rate of water mass evaporation in this case would be low, so this COP would be low. So these are the options for this one. I am audible. Yes. Why this? What? Audible?
Yes, sir.
Why it is causing a mute and unmute? Automatic change. Why it is taking place? Can you answer? Now it is all right?
Okay, sir. Okay, sir. You please share,
But
sir.
I just want to know why it is changing mode, automatic.
Maybe
I'm
your
not-
internet maybe bandwidth is low.
Oh, huh? Internet, I see. Okay. Anyway, are you, you can say, visible for
You
this?
please share, sir.
Okay, okay. 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 So I have just completed the vapor absorption part. Now, as I mentioned, that the another option is vapor adsorption cooling, and vapor adsorption cooling is based on adsorption process. Now, what is this adsorption process? It is just some kind of surface absorption, and mainly it is for hot and humid climate. For hot and humid climate, the comfort air conditioning can be achieved by using vapor adsorption or mist system. You can say x-axis and the specific humidity or humidity ratio on the y-axis, and we have, you can say 30%, 60%, 90%, 100%. This is complete lines like this one. So desiccant based cooling system offers an environment Am I audible?
Yes, sir.
So screen.
Share, sir. Please share the screen, sir.
Not able to share the screen. It
Not
says,
able to share the screen.
It says host disabled participant screen sharing. Can you please?
Yeah, sir. Wait, sir. Sir, please log out and log in.
Okay. We log back, it's still showing the same error message. Host disabled participant screen sharing. Please
But
check it.
from my side, nothing is shown, sir. It is everything is okay.
Okay, please check host disabled participant screen sharing.
No sharing option, sir.
Yeah, sharing option is not available. It's showing host disabled participant screen sharing. Audio video is fine, but sharing option is not there.
మీరు కాల్ చేస్తున్న వ్యక్తి వేరే కాల్లో మాట్లాడుతున్నారు.
So probably if you go to the screen share option, it will you can then say allow participant to also share the screen. That will enable this option. Everybody is new, yours is working. That is why it is not there. Red would have been inactive. Your black is fine, so it is active.
Yes. The screen is not being shown.
Okay, sir. But here also no option is available for me also.
So the admin of this group, they may be having the access.
Zoom is not.
We've just sent you a screenshot of the error message we are getting.
Sir?
Yeah, we've just sent a photo of the error message we are getting to, we sent it to you on WhatsApp.
Sir, otherwise you send your PPT to our mail, will share.
Okay.
Okay.
I think no option.
All right.
So at the initially I have given co-host for you, but no co-host is showing on the name of Kaushik sir.
Yes.
Something was happened.
Currently, it is showing RGM, HOD, ME as host and co-host both.
BSR RGM CET.
Yes.
BSR RGM CET.
సార్ ఒకసారి లాగిన్ సార్ మళ్ళీ లాగౌట్ లాగిన్ అవ్వండి సార్.
అయినాడు కానీ రాలేదు సార్.
అదే సెట్టింగ్స్ అయితే కనపడడం లేదు సార్. అది సార్ దాంట్లో సెట్టింగ్స్ ఉంటాయి సార్.
హలో. Sir, you are from?
Okay, so we will send the PPT over email to you and you will share it.
సార్ ఓకే సార్ సెండ్ సార్.
Okay, give me 2 minutes. No. So, okay, email has been sent. Please confirm once received. So email has been sent to the Gmail ID from which we received the invite for Zoom.
Sir, hello, sir. Sir, mail not came, sir.
Okay, so just wait. It will come in couple of minutes. It's been sent at the Gmail email ID.
I shared to you, sir, through chat. 99.Upendra.
Sorry, please come again.
Sir, 19@gmail.com.
Okay.
So, Have
you received? So, Professor Reddy, so have you received this, or we have sent at the Gmail ID, or would you want us to send at any other email ID?
You can send either to BSR RGM CET or 99.Upendra.
Can you just type this email address over WhatsApp?
Sir, please see in the chat box, sir.
Okay, chat box. Okay, this one. Oh, got it. Okay, so 99.upendra@gmail.com. So email has been sent. Let me know. Okay, let us know once you receive at 99.upendra@gmail.com.
So we received the mail, we are sharing, sir.
Okay. So then we want to Microsoft. Microsoft Team other duty distance.
Sir, how much time it will take, sir?
I will take about, I think, half an hour.
After at 2 o'clock, we have the another session, sir.
Okay, so you want me to finish? You can say I can take 15 minutes.
Yeah, you finish as early as possible, sir.
15 minutes.
Yeah, sir.
Yes.
So we'll share the PPT to the participants. So you finish in the meanwhile, sir.
Is it okay? So will you also share the PPT on screen, or we just refer to the page number and we continue with it?
Yes, sir. We are downloading. It takes 1 or 2 minutes, sir. In the meanwhile, you start, sir.
Okay.
So you can just tell about which page, Professor,
yes.
From page 59. So I think candidates can refer to page 59.
Okay, sir.
And we'll start from page 59, where we left.
Is it okay?
Will not see the screen, then refer it on their own screen. They have the PDF. Okay. Now you can just mention page number and then say I'm referring to this and then.
So I can start now?
Yes, you start, sir.
Okay. So as mentioned earlier, that vapor adsorption based desiccant cooling systems, they are for hot and humid climate, very much desirable because it is very simple in design as compared to vapor compression systems. So you can see the advantages of desiccant cooling systems where you can say high latent heat load is involved, and we have, you can say, better indoor quality, and you can say thermal energy as input source for especially the solar can be used for desiccant cooling systems as well, and for summer and monsoon air conditioning as well as winter heating options can be made available. So we have, you can say, we make use of adsorbent or desiccant materials, and the materials you can say suggested for solid adsorbents are silica gel, molecular sieves, alumina activated zeolite, and liquid adsorbents are aqueous solution of lithium chloride, calcium chloride, lithium bromide, and their mixtures. So we have a dehumidifier which is to be used, and this dehumidifier bed is you can say using a silica gel bed, and it is you can say As you can see that the bed is being rotated at a rate of 1 to 2 revolution per hour only. So we have two chambers. One is the process air chamber and the other is the, you can say, reactivation chamber. So this is the reactivation chamber and this is the process air chamber. So air to be dehumidified is first sent to this one, and then dehumidified air comes out. But this bed is rotating, so this portion now come on this side and this will come on this side. So hot air regeneration, hot air coming from, say, solar heated air or from electric heater or from auxiliary heater is coming, and then it will take away moisture from the bed and then it will go out. So in this way, dehumidifier operation is taking place. In India, Breyer, which is Breyer, part of Breyer USA, Breyer Asia or Breyer India, is manufacturing the desiccant beds, solid adsorbent dehumidifiers, and recommending the solid adsorbent cooling options. So a comparative study of a solid desiccant versus liquid desiccant, you can say solid desiccant systems are more compact, while liquid desiccant systems are more bulky. But we have a problem of high pressure drop in solid desiccant systems and lower pressure drop in the desiccant cooling systems. So in the desiccant systems, we have a surface absorption, while in liquid desiccants, we have volume absorption process. So which is a chemical phenomena, while in the solid desiccant systems are working on physical adsorption phenomena. So COP, you can say, for desiccant cooling systems are lower as compared to the liquid desiccant systems. So various cycles have been proposed. For solid desiccant cycles, ventilation cycle, modified ventilation cycle, and Dunkel cycle, and the solid, novel solid desiccant cycle. These are the options. While liquid desiccant systems are, you can say, based on Love cycle and validation cycle, liquid desiccant systems, and Godard and Jen cycles. So this is a simple ventilation. So what is the special feature of desiccant cooling systems is that we have a dehumidifier bed. You can say half portion of it is acting as a dehumidifier and half is as a regeneration. And similarly, we make use of the simple heat exchanger, air-air heat exchanger or air-water heat exchanger. And this is the air heater, where you can say where solar energy is to be used. And EC is the evaporative cooler. So on the basis of the psychrometric chart, you can say various state points which are shown in the cycle, they are shown on this one. So what we do, say for example, 1 to 2, we just dehumidify the air. So 1 to 2 is the air dehumidification. And then 2 to 3 is, you can say, cooling, and 3 to 4 is the evaporative cooling. And then 4 is the state where it is mixed with the state 6, and then mixed state is the supply air for the building. Now the return air is, you can say, at 4, which is evaporatively cooled, and then it is sent to the this air heat exchanger. It is preheated, and then the auxiliary heater or the solar air heater is being used to further heat it. So yeah, this is the heating through the heater, and then it is being, you can say, passed through this regeneration bed, and then it is being removed. So this is the process of the ventilation cycle, and the corresponding psychrometric chart process is shown here. So next cycle is the Dunkel cycle, which proposed that we may have a recirculation of the air. For example, we here we start to say return air evaporatively cooled, and then this heat exchanger, and then this through this dehumidifier, and then through this another heat exchanger, and then it comes back to the heat exchanger and evaporative cooler. So various state points are, you can say, shown on the psychrometric chart. And the problem is that the simplicity of the system is that we don't need mechanical compression. We don't need any air conditioning system. So we make use of the simple heat exchangers and a dehumidifier. Dehumidifier is the main component, and evaporative cooler, and a simple air heat exchanger. So with the help of this, we may, you can say, achieve cooling. And this is the modified cycle where we have combined both ventilation cycle and recirculation cycle. And the same process is shown on psychometric chart. So this is the new cycle which we proposed, and it makes use of the wet surface heat exchanger. This is the wet surface heat exchanger.
Sir, on which page you are, sir?
68.
68.
Now, first 67 and then 68.
Yes.
So 68 is liquid desiccant cooling system. It is similar to the solid desiccant system, except that here we have an absorber and a regenerator. So absorber is used to absorb moisture from the air, and regeneration is used to remove moisture from the, you can say, using the solution. So I need not, you can say, go into the details. These are the options using solid desiccant, liquid desiccant. I would just like to show, you can say, the novel cycle, hybrid cycle for air conditioning, where both, you can say, solid desiccant cycles can be used with vapor compression cycle, or liquid desiccant cycle where can be used with the vapor compression. And you can see the process involved here. I will just finish within 5 minutes. So you can say in conventional air conditioning system, what happens, that air is being cooled, and then moisture is being removed, and then reheating is being done. So we are able to reduce the moisture only through this, and it is just cooling the air, and then reheating is being done. Now in desiccant system, we make cooling through the vapor compression system, and then it is being supplied. It is a simple option. So hybrid air conditioning is desirable. It is these charts are shown on page 73. Now this is the hybrid, you can say, basic cooling cycle. So space, you can say, which is being cooled, and then a combination of a dehumidifier and this condenser and evaporator and this compressor heat. So by following the process of sensible cooling through the vapor compression system, and this is the, you can say, the solid desiccant cooling system, as you can see from different state points shown on this diagram. So this is solid desiccant hybrid space conditioning option, and simple operation, lot of energy saving can be achieved, and overall COP is higher for the hybrid air conditioning. So I need not go into details. So summary, solar collector systems which are being used for solar cooling systems, or especially for desiccant cooling systems. For an application is only for air conditioning, and the range, operating range for the various systems are given here. And then for the Thermex, you can say, vapor absorption machines, the systems are having different cooling capacity, more than 5 tons of refrigeration. And the market share for solar driven absorption chillers, as you can say, vapor absorption is covering now 71%, absorption system 13%, and desiccant system only 14%. That desiccant liquid systems only 2%. So a comparative study of these systems, or you can say simple economic analysis, you can say, of all cooling systems. One is the, for 1 kilowatt of cooling, we have made a comparative study and the comparative cost assessment. Photovoltaic vapor compression refrigeration based on solar, so it is costing 92,000. Then desiccant solar cooling systems costing 72,000, and vapor absorption solar cooling systems 7,600. Just to summarize, you can say the whole lecture or the summary, that for building air conditioning applications, new technology options are fastly coming up. These are addressing the need of less energy consumption and control comfort with little more cost. environmental concerns raised by vapor compression are being properly addressed by solar cooling options using vapor absorption, refrigeration, and desiccant-based cooling system. Hybrid system options are more energy efficient and lot of energy saving for air conditioning, and use of solar energy for cooling is found to be a viable option. Retrofitting of the building using passive space conditioning concepts and roof regeneration for open cycle absorption cooling is desirable from energy conservation point of view. Nowadays, heat pipe technology based integrated with solar cooling options is a new option which is coming up from the point of view of energy conservation, and HVAC industry may be having benefits from passive heat pipe technology along with active cooling technology systems. So that is all. Thanks for your kind attention. Please go through the PowerPoint presentations carefully, following the state points at different state points. You would be able to follow this one. Thank you very much. Your questions are most welcome.
Master.
Yes, is it okay?
Yes, sir. Yes, sir.
Okay. Any question, please? I'm sorry for the interruption due to the poor connectivity, internet connectivity. I don't know why it was causing so much. Either it was from your side.
Sometimes it is creating, sir. No problem, sir.
Yes.
I think.
I see. Okay. Okay.
Yes, sir. I think we are requesting participants. You have any doubts? You can ask now, or you give in a chat box. Sir will clarify. But majority.
Yes.
Can you share the PPTs, because there are a lot of interruption in between. We couldn't really connect.
We will provide. We will provide. Don't worry, sir.
Yeah, that will be fine if that is the case.
Yeah, we will provide. Yes. No doubt.
I have sent a PPT to Dr. Shiva Reddy, and he will circulate it. Yes.
Yes.
Okay, sir. Thanks a lot. Thank you very much.
I'm really very sorry why this interruption was there, and only last few PowerPoint presentations were not visible, while up to the vapor absorption, they were okay.
Whatever sir given the information, everything is published. All papers are published. Sir generally, mentality we know, he will open everything to the public. His attitude, that one. That's why he have more impact factor journals.
Everything is open. Yes.
Yes.
No
Yes, sir. Yes, sir.
Yes.
So, you have further any doubts, you can ask. I think.
Yes. Anyway, you circulate the PowerPoint presentations to the participants, and I think let them go through and try to understand a little bit more.
Yes, sir. Yes, sir. Yes, sir. No doubt.
Okay.
Once again,
does it happen every time?
Sir?
What I feel is that I think we are using Microsoft Team. That is a better platform rather than Zoom.
Yes, sir. Actually, we purchased this one, sir. That's why we are unable to purchase second one due to funds. Already we purchased Zoom.
Because I have been, I gave lecture to Dr. Manoj Gupta also, and Dr.
Yes.
Another with in Indore and everywhere. Everything was very, you can say, well organized like that. Yes. We were using Microsoft Team platform.
Yes. No problem, sir. Thank you very much, sir. You given your valuable time to us, and also you are the first lecture regarding introduction of renewable related.
Yes.
Related, sir. Once again, on behalf of RGM CET, we are expressing our sincere thanks to you, sir.
And also it is a great privilege. First time I got the opportunity for providing like this guest lecture, sir. With this, I am.
Okay. Thank you so much.
Thank you, sir.
Thank you. Okay.
Okay, sir. Thank you, sir. For the participants, note.
Thank you very much.
Thank you, sir. Yes, sir. For the participants, afternoon 2 o'clock, another lecture will start. He is also professor from IIT Kanpur, carbon capture and utilization and storage. So be on time. Thank you. Thank you very much, sir.
Okay. Thank you. Thank you, Dr. Shiva.
Thank you, sir. Thank you.
Okay. So I leave now. Can I leave now?
Sir, okay, sir.